Donut Lab has completed the first video in its series to prove its world's first solid-state battery, and it seems that the whole world is talking about it. So let's present this clearly to get an accurate picture of what is happening, because there is a lot of noise surrounding this story, and it is important to be extremely precise. To be honest, we cannot deny the breakthrough achievements that their solid-state battery can deliver, but at the same time, we want to analyze at least 4 points that need further clarification in their recent report. We are not saying that this battery is not good. In fact, it is very good. But when looking at the specific details, it is simply not as good as Donut Lab has claimed. So what exactly was Donut Lab right and wrong? First, Donut Lab is right. If you've watched their demonstration video of the charging speed, it is indeed impressive. Looking at the high C rates published by VTT, this battery is capable of handling charging currents of up to 11 C, reaching a full charge in about 5 to 6 minutes, or even 4.5 minutes as some reputable analyses have reported. At a 5C charging rate, it can reach 80% in under 10 minutes. These are impressive figures, considering that conventional batteries typically operate at around 1C to 2C. Even the fastest lithium-ion EV batteries today, whether LFP or NMC, cannot exceed 6C under ideal conditions. An 11C rate is quite extreme. Most people say this has been verified, but we don't think so. Before you get too excited, if you look a little more closely, there are several traps here, not just one. Donut Lab claims that its solid-state battery does not require extremely high clamping force to maintain the active layers and does not experience 15 to 20% swelling like other solid-state batteries. This helps reduce cost and complexity when assembling the battery pack. Accordingly, during testing, VTT conducted the evaluation on a single cell placed in an ideal laboratory environment. They did not verify the electrolyte, they did not open the cells, they did not drill, puncture, nail penetrate, or perform thermal compression tests like other battery tests have done. Nothing of that sort. As the presenter admitted, this test did not simulate operation within a real battery pack, but only represented a worst-case scenario for a single cell. There are still no results that accurately reflect performance when integrated into a larger system with concentrated thermal management challenges. After the test, the battery operated well even as temperatures rose, without the need for an active cooling system. Even when the temperature reached 192 degrees Fahrenheit at an 11C charging rate, the battery was still considered safe. However, 192 degrees Fahrenheit emitted from a single cell is extremely high. If thousands of cells were generating that level of heat simultaneously within the enclosed space of a battery pack without active cooling, the risk of fire, explosion, or damage to surrounding electronic components remains a major question. One particularly interesting point is that when the cooling system was reduced using only one cooling plate instead of two, the battery actually performed better. The higher temperature lowered the internal resistance, allowing it to sustain maximum charging current longer and reach full charge about 1 minute faster compared to when better cooling was applied. Yes, the battery did not explode, but it became extremely hot. Previously, Donut Lab marketed this battery as not requiring active cooling, but in reality, at 11C, passive cooling with just a heatsink is not sufficient. Let's compare this with real-world practice today. All high-performance EV batteries use sophisticated thermal management systems because high temperature is typically the #1 enemy of battery lifespan. The videos claim that poorer heat dissipation allowing the battery to reach nearly 194 degrees Fahrenheit actually improves charging speed may create a contradiction regarding long-term cycle life. The video focuses only on instantaneous charging speed and does not demonstrate whether repeatedly sustaining such high temperatures would rapidly degrade battery capacity. Those are two very different things. Continuous 11C charging in a real vehicle would certainly require serious thermal design. If multiple cells are assembled into a battery pack, the heat issue would be even worse. The temperature would not stop at 197 degrees Fahrenheit. It would rise much higher, and that is simply not sustainable, especially not for 100,000 charging cycles. If continuous 11C charging already pushes temperatures beyond sustainable limits. So why can this solid-state battery be commercialized in EV? Donut Lab has stated that it is the first company to integrate solid-state batteries into electric vehicles and commercialize them. VTT also clearly stated that these were cells identified by the customer as solid-state battery cells. However, their release timeline has shifted from within a few months in the announcement video released in early February to by the end of the year in the most recent confirmation video. We believe they also need to further explain how a team of around 9 employees could surpass companies like Cattle, Toyota, or Samsung, which have thousands of R&D staff and hundreds of PhDs. Their website homepage is now filled with comments such as, "This is a scam, not real, fake news, and nonsense." It's strange. It undermines their credibility. You would not see companies like BYD, KTEL, or Volkswagen doing that. VTT's report verifies only one thing: fast charging. That's it. The most controversial claims remain entirely unproven. The 100,000 cycles lifespan is the most radical assertion. In today's battery industry, even highly optimized lithium-ion cells typically achieve between 1,000 and 3,000 full charge cycles before experiencing significant capacity degradation. Some lithium iron phosphate chemistries can exceed that under favorable conditions, and advanced solid-state prototypes being developed by major global manufacturers have demonstrated several hundred to a few thousand cycles in laboratory settings. However, 100,000 cycles represents not a gradual improvement but an exponential leap. If a vehicle were charged once per day, such a battery could theoretically last more than 270 years. Even at 2 full charges per day, it would still exceed a century of operation. That would make the battery effectively permanent relative to the lifespan of most vehicles. The scientific challenge is that battery degradation is not optional. Every charge and discharge cycle introduces mechanical stress, electrode expansion and contraction, chemical side reactions, and gradual interface deterioration. Solid-state systems face additional hurdles, including interfacial resistance buildup between solid layers, microfractures in brittle electrolytes, and lithium dendrite formation during high-current charging. Donut Lab also claims ultra-fast charging capabilities, which would further intensify internal stress. Achieving 100,000 cycles under those conditions would require solving nearly every known degradation pathway simultaneously. Yet no long-term degradation graphs, extended cycle life datasets, or independent validation reports have been released to substantiate this number. The second headline specification is 400 watt-hours per kilogram energy density, compared to the 175 to 250 watt-hours per kilogram common in many premium lithium-ion electric vehicle batteries. 400 watt-hours per kilogram is extremely ambitious. While not theoretically impossible, it approaches the upper boundary of what experimental solid-state concepts have hinted at under controlled laboratory conditions. However, energy density is measured in two ways: gravimetric, expressed as watt-hours per kilogram, and volumetric, expressed as watt-hours per liter. Donut Lab has emphasized the 400 watt-hours per kilogram figure but has not disclosed the volumetric energy density. This omission is significant because vehicle battery packs are constrained by both weight and physical space. A cell may achieve high gravimetric density while sacrificing volumetric efficiency due to thicker separators, protective layers, or structural reinforcements. Without watt-hours per liter data, it is impossible to evaluate packaging efficiency or real-world integration feasibility. Further uncertainty emerged when a specification displayed at CES reportedly listed 350 watt-hours per kilogram instead of 400 watt-hours per kilogram. That discrepancy raises questions about testing standards, prototype variation, or measurement methodology. More importantly, the company has not explained how the 400 watt-hours per kilogram figure was achieved. There is no detailed disclosure of cathode chemistry, anode composition, lithium metal usage, or electrolyte classification. In solid-state battery research, the electrolyte is central to performance. Sulfide electrolytes may offer high ionic conductivity but suffer from moisture sensitivity. Oxide electrolytes provide stability yet tend to be brittle. Polymer-based systems can be flexible but often struggle with room temperature conductivity. Donut Lab has not clarified which class of material it employs, nor has it revealed any chemical formula or peer-reviewed research describing its approach. Okay. Just the energy density numbers alone are already enough to raise a huge question mark around Donut Lab. When a small company claims to break limits that have existed for decades but can't provide matching technical evidence, skepticism isn't just reasonable, it's necessary. And this is only the first red flag. We think what comes next might surprise you even more. Yeah, not only are the technical specs highly controversial, but Donut Lab itself, along with the CEO's background, has become a major source of concern for many experts and industry observers. So the query centers on whether sustaining an 11C charge rate, delivering 11 times the battery's capacity per hour, is feasible in real-world conditions for this innovative design. To unpack this, consider that a standard lithium-ion pack might hit 80 to 90% charge at 3 to 5C in lab tests. But real life brings heat buildup, lithium plating, and efficiency losses that cap practical rates far lower. At its core, 11C equates to extreme power demands for a 10 kilowatt-hours pack common in e-motorcycles, like those partnering with Donut Labs' Verge bikes. It means pumping in 110 kilowatts continuously. Donut's claims of 5-minute full charges imply rates around 10 to 12C for their high-density cells, as 400 watt-hours per kilogram enables smaller, lighter packs that tolerate aggressive currents without the liquid electrolyte vulnerabilities of old tech. Solid-state architecture shines here, replacing flammable liquids with stable ceramic or polymer electrolytes slashes internal resistance, allowing ion flow at blistering speeds while maintaining over 99% capacity from -22 degrees Fahrenheit to 212 degrees Fahrenheit. Early real-world tests on Verge motorcycles confirm stable operation under load, with no fires even if punctured, suggesting 11C isn't mere hype. Yet practicality hinges on layers beyond the lab. Heat management is pivotal. Even solid-state batteries generate localized hotspots at 11C, risking dendrite formation or electrolyte cracking if cooling liquid or air can't dissipate 100+ kilowatts per square meter peaks. Infrastructure lags. 2 public chargers top out at 350 kilowatt DC, but scaling to over 500 kilowatt for 11C on larger packs demands grid upgrades and beefy cables, unfeasible in most regions today. Cycle life holds up impressively, 100,000 versus 5,000 for lithium-ion, but sustained 11C could accelerate wear from mechanical stress on the rigid stack design, especially in vibrations from real vehicles. Comparisons ground this. Tesla's 4,680 cells push 5 to 7C peaks briefly, but average 2C for Cybertrucks. Donut's donut-shaped cells optimized for hub motors reportedly sustain higher via spintronic nanocarbon interfaces. Per forum tests. In Vietnam's humid tropics or Thai Nguyen's winters, thermal stability gives Donut an edge over Leon's 20 to 30% range loss. OEM scaling is underway at gigawatt-hour levels, with CES 2026 demos proving commercial viability for e-bikes first. Ultimately, 11C is feasible for Donut's batteries in controlled, small-pack scenarios like motorcycles. Real tests show it works without catastrophe. For cars or trucks, its aspirational needs better cooling, chargers, and validation beyond 2026 pilots. If Donut delivers on promises, it redefines fast charging as routine, slashing EV adoption barriers. So why is Donut Labs' solid-state battery struggling to gain market trust? The absence of transparency extends to manufacturing and cost claims. Donut Labs states that its battery avoids cobalt and nickel and relies on more abundant materials, implying lower production costs than conventional lithium-ion systems. However, material cost is only one component of total battery economics. Solid-state cells often require specialized dry room environments, new assembly techniques, precise pressure control during stacking, and entirely different production lines compared to liquid electrolyte lithium-ion cells. Yield rates during early manufacturing phases can dramatically influence real cost per kilowatt-hour. Without information about production partners, pilot lines, factory infrastructure, or capital expenditure models, claims of cost parity or cost advantage remain projections rather than demonstrated outcomes. The battery has been described as ready for mass production, yet no factory, production line, or large-scale manufacturing partner has been identified publicly. Donut Lab is an extremely young company, registered in Estonia, with a reported headcount of only about 9 employees as of late last year. Based on publicly available information, just one member of the team appears to have a technical background directly related to battery technology. The rest primarily come from sales, marketing, startup operations, or project management. This stands in sharp contrast to how any serious battery manufacturer typically operates. Major battery producers usually employ hundreds, if not thousands, of materials scientists, chemists, and electrochemical engineers who spend years working to improve performance by just a few percentage points. So the question is, how could a company with such limited resources achieve what would be considered the most significant technological breakthrough in the history of batteries? Donut Lab is an extremely young company, registered in Estonia, with a reported headcount of only about 9 employees as of late last year, based on publicly available information. Just one member of the team appears to have a technical background directly related to battery technology. The rest primarily come from sales, marketing, startup operations, or project management. This stands in sharp contrast to how any serious battery manufacturer typically operates. Major battery producers usually employ hundreds, if not thousands, of materials scientists, chemists, and electrochemical engineers who spend years working to improve performance by just a few percentage points. So the question is, how could a company with such limited resources achieve what would be considered the most significant technological breakthrough in the history of batteries? Another questionable sign is Donut Labs' choice of its first commercial partner. Instead of collaborating with major automakers, global battery manufacturers, or large industrial groups capable of conducting rigorous technical due diligence, Donut Lab chose a small electric motorcycle company with very limited revenue as its showcase partner. Specifically, the company integrated its solid-state battery technology into the high-end Verge TS Ultra electric motorcycle. This was presented as a revolutionary leap forward in EV performance. With a claimed energy density of 400 watt-hours per kilogram, the new battery is said to enable a range of up to 370 miles on a single charge, far beyond current industry standards. Even more striking is the ultra-fast charging capability, reportedly allowing a full charge in just 5 minutes, comparable to refueling a gasoline vehicle. It certainly sounds exciting, but we remain skeptical. This runs counter to basic business logic. If you truly possess a world-changing battery technology, you would not debut it with a niche manufacturer. Instead, major corporations would be lining up to secure partnership agreements. The most debated claim is the 100,000 cycles lifespan. In today's industry, even optimized lithium-ion batteries typically achieve 1,000 to 3,000 full cycles. Advanced lithium iron phosphate systems may exceed that, and solid-state prototypes from major developers have demonstrated several hundred to a few thousand cycles. But 100,000 full cycles would represent an unprecedented leap. Researchers online are asking what definition of cycle was used. If the figure is based on shallow partial cycling, it cannot be compared directly with full-depth automotive usage. Without published long-term capacity retention data, the number remains unverified. Energy density is another focal point. Donut Lab promotes 400 watt-hours per kilogram, a level approaching the upper boundary of experimental solid-state research. Established players such as Toyota and CATL have announced ambitious targets but remain cautious about commercialization timelines. Analysts note that Donut Lab has not disclosed volumetric energy density, cathode composition, electrolyte type, or peer-reviewed research. Without that transparency, it is difficult to evaluate integration feasibility at pack level. Manufacturing scalability also fuels skepticism. Companies like Samsung SDI and QuantumScape have spent years refining pilot production lines before discussing mass deployment. Solid-state batteries introduce challenges in pressure control, interface uniformity, and defect management. Donut Lab has not publicly identified a large-scale factory, pilot line, or manufacturing partner. In an industry where yield rates determine cost viability, this absence is significant. The partnership with Verge Motorcycles and integration into the Verge TS Ultra generated attention. But critics question why a breakthrough of this magnitude would debut with a niche manufacturer rather than a global automaker. Combined with shifting commercialization timelines, this has intensified online skepticism. So if this is truly a historic breakthrough in battery technology, why hasn't it partnered with major players like Toyota or KTL from the beginning? Please share your opinion in the comments section below this video. Thanks for watching our video. Subscribe now so you don't miss the next breaking Tesla update. It's coming in just 2 days. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Are solid-state batteries really safe? You might assume that ultra-fast charging would make them volatile or dangerous, but the evidence suggests otherwise. In a demonstration of BYD's new BYD Blade battery, the battery was deliberately short-circuited after already completing 500 charge cycles. The result: no explosion, no fire, not even smoke even after 2 hours. For many people, that kind of safety test raises an even bigger question if battery technology is advancing this quickly. Could someone eventually solve the biggest problems that have held modern batteries back for decades? That's exactly why a new claim from a small startup called Donut Lab is starting to attract so much attention. According to the buzz online, its so-called revolutionary battery could deliver a 100,000-mile lifespan, recharge in just 5 minutes, and remain completely safe even at temperatures as high as 100 degrees Celsius. Naturally, the internet is fascinating. If you search for Donut Lab's battery technology, you'll find countless videos and articles discussing its extraordinary performance claims. Some say it can charge at incredible speeds. Others claim it can survive temperatures that would normally destroy conventional batteries. And then there are the numbers tied to its energy density and lifespan figures that sound almost too good to be true. So the big question becomes, how could Donut Lab be building the next generation of batteries? Or is this another case of hype racing far ahead of reality? Before we go any further, there's something important you should know. Donut Lab has just released the results of its second independent battery test, and the numbers coming out of that test are strange. Not because the battery failed. It didn't. In fact, the opposite happened. According to the data, the battery actually delivered more capacity when it was exposed to extreme heat. The cells were heated to around 100 degrees Celsius and then discharged. And instead of degrading as almost every conventional lithium-ion battery would, the performance improved. That's where things start to get confusing. Because what appears in the test data doesn't neatly support either side of the debate. On one side, critics believe the technology is unrealistic and possibly exaggerated. On the other side, supporters believe Donut Lab may have built a revolutionary battery capable of changing the entire EV industry. But the strange part is that this new test seems to contradict both groups at the same time. When analysts began examining the results closely, they discovered details that were not immediately obvious in the official report. Every data point was rechecked. Calculations were performed on parameters that were never explicitly mentioned. And the performance of this cell was compared against nearly every commercial battery that currently exists on the market. Then the investigation went even deeper. Researchers began reviewing published academic papers, analyzing thermal performance data, and even looking into the supply chain behind the company's battery materials. What they found opened up a number of fascinating possibilities and raised even more questions. So before we dive into the technical tests, let's first understand what Donut Lab actually is. Donut Lab is a small Estonian-Finnish startup that has made some incredibly bold claims about its battery technology. According to the company, it has developed a solid-state battery that doesn't rely on lithium, a statement that immediately caught the attention of engineers across the world. The company says its battery could potentially charge from 0 to 80% in just 5 minutes. It also claims the battery could survive up to 100,000 charge cycles, dramatically exceeding the lifespan of current lithium-ion batteries. Donut Lab states that its battery could reach 400 watt-hours per kilogram. If that number is accurate, it would significantly outperform most commercial EV batteries currently available. To put this into perspective, many electric vehicle batteries today operate in the range of 200 to 300 watt-hours per kilogram. Reaching 400 would represent a massive leap forward in energy storage technology. If all of these claims turned out to be true, the implications would be enormous. Electric vehicles could charge faster than it takes to refuel a gasoline car. Range anxiety could disappear almost entirely. And battery packs could last for decades without significant degradation. Naturally, when a startup claims to achieve all of these breakthroughs simultaneously, skepticism follows immediately. That's why Donut Lab began publishing independent test results. In an earlier experiment, the company worked with Finland's National Research Center to test one of its prototype cells. That first test already sparked intense debate because the battery showed a voltage profile that looked surprisingly similar to traditional lithium-ion chemistry. The average discharge voltage measured in that experiment was around 3.5 volts, a value commonly associated with NMC lithium-ion batteries. So if the battery truly contains no lithium, why does its electrical behavior resemble lithium-ion cells so closely? That question remains one of the biggest mysteries surrounding this technology. Now, the second test has arrived, and this time the focus shifted towards something even more dramatic. Before we examine the results, it's important to understand how the test was conducted. The experiment was carried out by an independent research organization in Finland. However, their role was not to prove or disprove the technology. They simply tested the device provided by Donut Lab and followed the testing plan requested by the company. In other words, the researchers were verifying measurements, not validating the broader claims about the battery's chemistry. For the experiment, a single cell labeled DL2 was placed inside a climate chamber where temperature conditions could be precisely controlled. A 2.4 kilogram steel plate was positioned on top of the battery to apply mechanical pressure during the test. This pressure was relatively small compared with what many solid-state batteries require, suggesting it was mainly used to prevent uneven heating rather than to influence the electrochemical reactions inside the cell. At room temperature, the battery was charged and discharged normally. During this baseline measurement, the cell delivered approximately 24.9 amp-hours of capacity. So far, nothing unusual. But everything changed once the temperature began to rise. After the baseline test, the climate chamber temperature was increased to 80 degrees Celsius and held there for 2 hours. The battery remained inside the chamber during this time to ensure that its internal components fully stabilized at the elevated temperature. Once the cell had reached thermal equilibrium, it was discharged again. And that's when something surprising happened. Instead of losing capacity as most batteries would at higher temperatures, the cell delivered 27.5 amp-hours. which corresponds to roughly 110% of its room temperature capacity. In other words, the battery actually performed better when it was hotter. Even more interesting, the researchers then repeated the process under even more extreme conditions. The chamber temperature was raised again. This time it reached 100 degrees Celsius. Yet during this test, the Donut Lab battery continued to operate. The cell was discharged again, and the measured capacity reached 27.6 amp-hours, still higher than the room temperature reference measurement. However, one important detail was noticed after the 100 degrees Celsius test. The battery pouch had lost its vacuum seal. Photographs from the test show that the pouch visibly expanded, suggesting that gas had formed inside the cell or that the packaging material had weakened under extreme heat. Interestingly, despite the compromised pouch structure, the battery continued functioning normally when charged afterward. This observation may reveal something fundamental about the internal chemistry of the cell. If the battery contained a typical lithium-ion electrolyte, a breach in the pouch at such a high temperature would likely lead to serious problems. Liquid electrolytes used in lithium-ion batteries often contain organic solvents that are highly flammable. At temperatures approaching 100 degrees Celsius, these solvents can vaporize. Combined with oxygen from the air and elevated heat levels, this creates the conditions necessary for combustion. How does Donut Lab's battery survive 100 degrees Celsius if the battery had contained a conventional lithium-ion electrolyte? A breach in the pouch at such a high temperature could have created serious problems. Most lithium-ion batteries rely on liquid electrolytes made from organic solvents, many of which become volatile when heated. Under extreme conditions, these materials can vaporize and react with oxygen in the air, creating a serious safety risk. But in this case, none of that happened. The battery continued operating even after the pouch seal had failed. That observation alone suggests that the internal chemistry of the Donut Lab cell may be fundamentally different from traditional lithium-ion batteries. And that realization led researchers to take a closer look at the rest of the test data. When analysts began examining the measurements more carefully, several unusual patterns began to appear. The first involved Coulombic efficiency, a metric that measures how much electrical charge enters a battery compared to how much energy can be extracted from it. It is one of the most important indicators of long-term battery health. At room temperature, the Donut Lab cell achieved a Coulombic efficiency of approximately 99.82%, which is already quite strong for a prototype battery. When the temperature was raised to 80 degrees Celsius, the efficiency dropped slightly to 99.18%. That change is expected, since higher temperatures typically accelerate small side reactions inside battery materials. But after the battery cooled back down and was cycled again at room temperature, the efficiency recovered to 99.88%. In other words, the battery appeared to recover from the thermal stress rather than suffering permanent degradation. In most conventional lithium-ion cells, repeated exposure to extreme heat would gradually damage the electrolyte and internal structures, causing efficiency to decline over time. The behavior observed here suggests that the Donut Lab battery may be using a different chemical system. A second anomaly appeared in the battery's internal resistance. As the temperature increased from room temperature to 80 degrees Celsius, the internal resistance of the cell dropped by about 18%. At first glance, this might seem completely normal. Higher temperatures generally allow ions to move more easily through the electrolyte, reducing resistance. However, typical lithium-ion batteries often show resistance reductions closer to 40% over a similar temperature range. The smaller change observed here suggests that the electrolyte inside the Donut Lab cell may behave differently from the liquid systems used in conventional lithium-ion batteries. These observations led researchers to consider another possibility. What if the battery doesn't use lithium at all? At first, that idea seemed unlikely. Earlier testing showed an average discharge voltage of about 3.5 volts, which strongly resembles the voltage profile of NMC lithium-ion batteries. Most sodium-ion batteries operate closer to 2.8 to 3.1 volts, making them appear very different from lithium systems. But further investigation revealed something interesting. Certain types of layered sodium-ion cathode materials can actually produce voltage curves that look surprisingly similar to lithium-ion NMC cells. These materials can approach average discharge voltages of roughly 3.5 volts, and their discharge curves can appear smooth rather than stepped. That discovery opened the door to a new hypothesis. If Donut Lab is using an advanced sodium-ion architecture, it could explain several of the unusual behaviors seen in the test results. Sodium-ion batteries are generally more thermally stable than lithium-ion cells, with thermal runaway thresholds that can exceed 130 degrees Celsius. Some experimental sodium-ion designs have even demonstrated improved performance at elevated temperatures. That kind of chemistry could help explain why the Donut Lab cell delivered higher capacity at 80 degrees Celsius. Another clue emerged from materials research. Investigators examining the company's potential supply chain found references to carbon nanotube structures coated with titanium oxide, paired with a sodium-based electrolyte. Titanium oxide is already a well-known anode material in sodium-ion battery research. When combined with highly conductive carbon nanotube networks, it can form a structure capable of supporting efficient ion transport even under demanding conditions. In theory, an architecture like this could produce exactly the kind of thermal behavior observed during the high-temperature tests. But there is still a major problem with that explanation. Energy density. Today's best commercial sodium-ion batteries typically achieve around 160 to 175 watt-hours per kilogram. That's significantly lower than modern lithium-ion batteries used in electric vehicles. Yet Donut Lab claims its battery could reach 400 watt-hours per kilogram. If that figure is accurate, it would be more than double the performance of current sodium-ion technology. And that means the puzzle is far from solved. At this point, the evidence leads to a complicated conclusion. Some aspects of the battery's behavior don't match conventional lithium-ion chemistry, but the company's claims also go well beyond what sodium-ion batteries have demonstrated so far. The real answer may lie somewhere in between, or possibly in an entirely new hybrid architecture. So what do we actually know for certain? After 2 independent tests, several facts appear clear. The battery survived exposure to 100 degrees Celsius while fully charged. It delivered more than 100% of its baseline capacity at elevated temperatures. It continued operating even after its pouch seal failed. And its efficiency and resistance patterns suggest that its internal chemistry may differ from traditional lithium-ion cells. At the same time, many of the company's biggest claims remain unverified. The battery has never been publicly weighed, which means the 400 watt-hours per kilogram energy density cannot yet be confirmed. The tests included only 13 total charge-discharge cycles, far short of the 100,000 cycle lifespan the company advertises. And perhaps most importantly, the battery was never charged at high temperature, it was only discharged under those conditions. That detail matters because charging is typically the most stressful part of battery operation. If the cell can truly tolerate charging at 100 degrees Celsius, that would represent an extraordinary breakthrough. But until that test is performed, the question remains unanswered. For now, we know that at least 3 prototype cells have been sent for independent testing. One was used in the first experiment, another was used in the high-temperature test, and a third cell is reportedly scheduled for future evaluation. Some analysts believe the next experiment could focus on low-temperature performance, possibly testing the battery at temperatures as low as -30 degrees Celsius. If the cell can truly operate across a range from -30 degrees Celsius to 100 degrees Celsius, it would dramatically narrow the list of possible battery chemistries and potentially represent one of the most impressive energy storage technologies ever demonstrated. For now, however, the industry remains cautiously curious, because in the world of energy technology, bold claims appear all the time, but genuine breakthroughs are far more rare. So the question still remains, is Donut Lab quietly building the future of batteries? Or are we witnessing another chapter in the long history of ambitious energy startups promising more than physics will allow? Fortunately, we may not have to wait very long to find out. If these batteries eventually begin appearing inside real electric vehicles, engineers around the world will finally have the opportunity to analyze them directly. And when that happens, the truth will become impossible to hide. It is difficult to imagine that a small startup in Finland could quietly solve the solid-state battery challenge, while heavily funded industry giants, after spending billions on research and development, have yet to achieve anything close to these performance targets. This is exactly why a well-known scientific principle becomes especially relevant. Extraordinary claims require extraordinary evidence. In the case of Donut Lab, this principle is more than a simple warning. It is the only reliable filter separating a genuine energy breakthrough from a technological illusion. By claiming to have developed a lithium-free battery with an energy density of 400 watt-hours per kilogram, a 5-minute charging time, and a lifetime of up to 100,000 cycles, Donut Lab is challenging nearly every physical and chemical limitation that battery researchers have spent decades working within. If true, such a technology would address almost all of the electric vehicle industry's biggest challenges at once: range, charging speed, and long-term durability. So far, however, The available evidence remains promising but not extraordinary. Test results reported by Finland's VTT Research Center indicate that the battery can operate stably at 100 degrees Celsius, which is certainly encouraging. But this alone does not confirm the more ambitious claims, such as 400 watt-hours per kilogram energy density or 100,000 charging cycles. In science, transparency must match the boldness of the claim. Leaving out key information such as the actual weight of the battery cell or avoiding tests like high-temperature charging creates uncertainty. To some observers, it feels a bit like watching a magician ask the audience to focus on one hand while the real trick happens in the other. That said, history shows that groundbreaking innovations sometimes emerge from small, unconventional teams. For that reason, the most reasonable approach is neither blind belief nor immediate dismissal, but cautious openness. With more independent testing and transparent data, we will eventually discover whether Donut Lab is building the future of battery technology or simply presenting an ambitious idea that has yet to overcome the realities of physics. So what do you think? Please share your opinion in the comments section below this video. Thanks for watching our video. Subscribe now so you don't miss the next breaking Tesla update. It's coming in just 2 days. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to turn on notifications so you never miss our latest videos.
Yeah, so I guess I'll start with that. In terms of the semi, that's going quite well, and that's the first step to obviously getting autonomous trucks on the road.
According to Tesla's latest announcement, the Tesla Semi will become the world's first fully self-driving truck with a total weight of up to 80,000 pounds. Nearly 9 years after its debut, the Tesla Semi was once considered the most challenging vehicle Tesla had ever built. But now, everything has completely changed.
Factory is going on schedule. We've completed the building and are installing the equipment now. We've got our fleet of validation trucks driving on the road. We'll have larger builds towards the end of this year, and then our first online builds in the first part of next year, ramping into the Q2 timing with real volume coming in the back half of the year.
The mass production line at Giga Semi is nearly complete, and Tesla will be able to build a truck like the Semi in just 10 to 15 minutes. Starting from late 2025, anyone, not just major logistics companies, will be able to order a Tesla Semi. The company announced an expected production of at least 10,000 units by the end of 2025, aiming to reach 50,000 units in 2026. According to Dan Priestley, this fully self-driving version is not only more powerful and quicker to accelerate, with an all-new, insanely low drag coefficient, but also significantly more affordable, thanks to at least 6 major improvements in its manufacturing design. So, how does the fully autonomous Tesla Semi actually work? What design changes were made for mass production? And is its price really as groundbreaking as it sounds? Welcome to Tesla Car World. The Tesla Semi continues to draw widespread attention with its outstanding performance, standing out even in its early test runs compared to traditional diesel trucks. However, what we've seen so far is only the initial testing phase. Currently, all operating semi-trucks are prototypes, delivered to a select group of strategic customers for real-world testing and data collection. This crucial stage is designed to refine the final design before Tesla transitions to full-scale production at its new facility later this year. It seems Tesla is making a serious push to develop full self-driving FSD for the Tesla Semi. This was hinted at in a recent video that appears to show a Tesla Semi engineering unit equipped with sensor arrays, possibly undergoing real-world FSD calibration. A short video featuring the unique Tesla Semi engineering team has been shared online across several news platforms. According to the latest reports, the Tesla Semi engineers were driving on public roads when the footage was captured. The discovery of the mysterious Tesla Semi engineering unit has been met with enthusiasm by the EV community. Some believe that the development of the FSD system for the fully electric Class 8 truck could accelerate thanks to Tesla's ongoing investments in AI. After all, with full self-driving capability, the Tesla Semi could truly redefine long-haul trucking, offering a vehicle that's significantly safer and far more cost-efficient to operate than any other Class 8 truck on the road today. Interestingly, the Tesla AI team recently teased the upcoming deployment and release timeline of FSD for the Semi. Amid the excitement surrounding the rollout of FSD for the Cybertruck, several social media users began asking when this advanced driver assistance system would also be available on the Tesla Semi. In response to one of these questions, the Tesla AI team revealed that the Semi's FSD build is now in its final version and is expected to launch by the end of this year. However, widespread deployment will likely take a bit longer, potentially until the second quarter 2026, when Tesla may begin offering it to individual customers, not just major logistics companies like other commercial brands. Although Tesla isn't the only company producing electric trucks, others include Volvo, Mercedes-Benz, Packard, Daimler, and BYD. It's almost laughable that none of them can truly compete with the Tesla Semi. That's not to say those electric trucks aren't good. They simply don't come close to the level of performance and innovation delivered by the Semi. Put simply, the Tesla Semi is the only electric truck capable of traveling 800 miles on a single charge, accelerating from 0 to 60 miles per hour in just 20 seconds, even when carrying a total load of 80,000 pounds. And when it's not loaded, the Semi has been confirmed to maintain that same 800-mile range, a feat no other electric truck can match. The excitement around Tesla's next-generation semi-truck continues to build, and for good reason. The upcoming second-generation Tesla Semi isn't just about speed or raw power. It's a comprehensive evolution, packed with advanced upgrades that will likely redefine what commercial electric trucking can achieve. These enhancements aren't merely technical. They represent Tesla's continuous push to make long-haul transportation cleaner, smarter, and more efficient. Of course, the truck's futuristic look still sparks debate. Some love its sleek aerodynamic design, while others prefer the rugged appearance of traditional diesel rigs. And that's perfectly fine. Innovation always divides opinion. Tesla actively welcomes this kind of feedback, encouraging drivers and enthusiasts to share their thoughts. After all, community input has played a huge role in shaping Tesla's vehicle development over the years. Now, let's get into the real engineering breakthroughs that set the new Semi apart. Beyond a few refined performance tweaks, the biggest change lies under the surface, in the all-new battery architecture that will power Tesla's latest generation of electric trucks. According to Tesla's Master Plan Part 3, the long-range version of the Semi currently uses an 800 kilowatt-hour battery pack made with high-nickel NMC chemistry. This setup allows it to achieve the remarkable range figures that have captured industry attention. Meanwhile, the shorter-range variant, nicknamed the Semi Lite, is powered by more affordable and durable lithium iron phosphate cells, offering a practical balance between cost and efficiency. However, the most significant leap forward comes with Tesla's plan to introduce its cutting-edge HV cells, better known as the 4680 battery cells, into future Semi models. These next-generation cells promise higher energy density, improved thermal management, and lower production costs. In other words, they're the key to making electric freight transport both more powerful and more economically viable. What's even more impressive is that despite these changes, the Semi's outstanding range remains intact. Tesla achieved this through a roughly 7% improvement in overall efficiency, thanks to refined aerodynamics and design optimization. With the new setup, the truck can carry a smaller and lighter battery pack without compromising performance. This translates to reduced weight, better handling, and lower operational costs, a major advantage for fleet owners looking to save on both energy and maintenance. Many analysts long suspected Tesla would eventually adopt the 4680 cells for the Semi, and it's easy to see why. It wouldn't make sense to reserve Tesla's most advanced battery technology solely for vehicles like the Cybertruck. The 4680 cells offer exactly what heavy-duty electric trucks require: high output, energy efficiency, and scalable cost savings. Production efficiency is also on Tesla's side. Since the company manufactures these cells directly at the Nevada Gigafactory, assembly and integration of the Semi's battery systems are faster and more streamlined than ever before. This vertical integration helps Tesla control quality, reduce logistics complexity, and accelerate deployment timelines. In addition to the mechanical and electrical improvements, Tesla has made several design refinements aimed at real-world usability. Dan Priestley, one of the key figures behind the Semi program, recently shared details about new side mirrors that enhance visibility and improve airflow. The updated cabin now includes drop glass, a redesigned windshield and side window system that provides drivers with a clearer field of view while boosting aerodynamics. The current prototypes feature traditional mirrors equipped with integrated cameras connected to a camera monitoring system. These feed live video to dual 15-inch interior displays, giving the driver a comprehensive 360-degree panoramic view of their surroundings. This setup not only satisfies regulatory requirements in the US, but also effectively eliminates blind spots, a huge step forward in trucking safety. The drop glass addition may sound small, but it's a big deal in practical terms. Since the driver's seat is centrally positioned, interacting with people outside, at checkpoints or delivery gates, used to require opening the entire door. The new roll-down window feature fixes that inconvenience, making daily freight operations smoother and more ergonomic. Tesla Semi's price shock. What's the real breakthrough Tesla is hiding? The Tesla Semi will be offered in two range configurations, 500 miles and 300 miles. Both variants will now feature redesigned side mirrors and drop-down windows to improve driver visibility and streamline interactions with external systems, such as terminal control panels at shipping ports. Previously, trucking companies that wanted to own a Tesla Semi had no choice but to pay extra for the standard 500-mile version, even if their daily routes were limited to short-distance hauls, like urban deliveries or regional logistics. This created a financial burden for many small and medium-sized businesses, especially when they couldn't fully utilize the truck's long-range and premium capabilities. However, with Tesla's new configuration options, the Semi can now be customized to meet the specific operational needs of each business. For example, base versions with ranges between 250 and 300 miles are now available, ideal for short-haul transport. This added flexibility allows customers to avoid paying for unnecessary features while still benefiting from the core advantages that make the Tesla Semi so compelling. Low operating costs, powerful performance, and eco-friendly design. Even the base models retain Tesla's signature qualities: durable electric motors, impressive acceleration, and aerodynamic styling that enhances energy efficiency. By scaling back premium features such as extended range and advanced driver assistance systems, Tesla has significantly reduced the upfront cost, making electric trucking more accessible and practical for a wider range of businesses. Tesla introduces two trims of the Semi at the end of 2025. The right pricing will make diesel feel like yesterday's technology to even the most hard-nosed fleet manager. The men who sign purchase orders for tractors do not buy hype. They buy lower cost per mile, higher uptime, and a payback period they can explain to an accountant. On that score, a two-trim strategy can hit both the value buyer and the performance buyer, with prices that bracket today's heavy-duty Class 8 diesel tractors and undercut most battery electric competitors once the real costs are tallied. Imagine a standard range version with roughly 300 to 350 miles between charges and a manufacturer's suggested retail price of $199,000, and a long-range version with roughly 500 miles between charges at $249,000. Those sticker prices overlap well-spec'd new diesel tractors that often run between $150,000 and $200,000, while staying below many battery electric rivals that end up far north of $300,000 in practical configurations. Now layer in the federal commercial clean vehicle credit, which has reached up to $40,000 for heavy-duty zero-emission trucks. With that credit alone, the effective entry price on the standard range falls to about $159,000. In the right states and with volume deals, it is realistic to see offers that start with $149,000. That is the shock number that wakes up a skeptical buyer. A brand new electric Class 8 tractor effectively in the $149,000 to $159,000 lane. Operating math is where minds change. A typical long-haul diesel returns about 6 to 7 miles per gallon. At $4 per gallon, you spend roughly 60 to 67 cents per mile on fuel. Tesla has pointed to energy use under 2 kilowatt-hours per mile. Think about 1.7 to 1.9 kilowatt-hours per mile. If fleet or off-peak electricity is 10 to 15 cents per kilowatt-hour, the energy cost works out to about 17 to 28 cents per mile. Even after you average different lanes and charging situations, you are very reasonably 30 to 40 cents per mile better than diesel on energy alone. Roll 100,000 miles per year, and that is $30,000 to $40,000. Saved annually before you touch maintenance. Maintenance pushes the gap wider. Electric powertrains have far fewer moving parts, no oil changes, no diesel particulate filters or diesel exhaust fluid systems to babysit, and regenerative braking that reduces wear on friction brakes. A cautious estimate is 10 to 15 cents per mile saved on maintenance. Add that to the energy advantage, and you are 40 to 55 cents per mile ahead of diesel. At 100,000 miles per year, you are saving $40,000 to $55,000 every year. That wipes out the initial price premium in 2 to 3 years after incentives. Owner-operators and small fleets that keep tractors for 5 to 7 years will see the cumulative cash advantage compound quickly. performance matters to drivers and dispatchers. Tesla has claimed 0 to 60 miles per hour in roughly 20 seconds at a gross weight of 80,000 pounds and the ability to hold about 60 miles per hour on 5% grades. In real terms, that means steadier schedules, fewer slow crawls in the right lane on climbs, and less time lost in mountain corridors. 3 independent drive motors mean instant torque at the wheels that matter and better traction when weather turns ugly. The charging profile associated with the megacharger concept has discussed power levels up to roughly 1 megawatt and demonstrations around 30 minutes to reach about 70% charge, which keeps utilization competitive for tight turns or driver swaps. If your network revolves around out-and-back spokes of 250 to 300 miles, the standard range at an effective $149,000 to $159,000 is the budget wrecking ball. If you run true regional or longer lanes and want 450 to 500 miles between stops, the long range at $249,000, or about $209,000 after the federal credit, still drives a faster payback than a diesel. Once you cross roughly 80,000 to 100,000 miles per year, payload is a fair concern. Battery electric Class 8 tractors weigh more, but federal rules have allowed up to 2,000 pounds of additional gross weight for zero-emission vehicles, which narrows the penalty. In many freight profiles, shippers run out of trailer space before they hit weight limits, especially with packaged goods, parcel, or lighter refrigerated loads, so the penalty often matters less than it appears on paper. Charging and site planning are the practical hurdles, yet many fleets already stage tractors at depots. Pairing overnight charging with midday top-offs keeps utilization high without relying solely on public infrastructure. Diesel still enjoys a station on every corner, but private behind-the-fence chargers at the yard put energy right where the trucks sleep. Put simply, if Tesla lands those 2 price points, the Semi stops being a science project and becomes the default specification for high-mileage lanes. The standard range delivers the shock-low entry that beats diesel on total cost from day one, and the long range delivers speed on grades and range confidence while still paying back in 2 to 3 years at real annual mileage. For American men who run the numbers and pull the hills, that is the persuasion that matters. The year 2025 is shaping up to be a defining moment for Tesla, as production of the semi-truck ramps up at an unprecedented pace. The company has set an ambitious goal of building at least 10,000 units before the year ends. Looking ahead to 2026, Tesla aims even higher with a target of 50,000 trucks, though reaching that full figure may take time. Still, one thing is beyond doubt. By the close of this year, 10,000 Tesla semis are expected to roll off the production line. Tesla remains firmly committed to delivering every outstanding order to customers who have been waiting patiently for years. Elon Musk has long stressed that businesses choosing not to adopt the Tesla Semi are potentially leaving huge profits on the table. With its groundbreaking energy efficiency, lower fuel expenses, and minimal maintenance requirements, the Semi isn't just another truck, it's a revenue-generating powerhouse on wheels. The best part? Tesla plans to make the Semi available to a much broader customer base in the near future. And Tesla is offering customizable configurations for the Semi, allowing fleets to tailor their trucks based on performance needs and budget constraints. Early users have consistently praised the vehicle's exceptional power, range, and reliability. If Tesla stays on course, by 2026 the Semi could redefine the global trucking industry, proving once and for all that electric trucks can outperform their diesel counterparts. So what do you think about the current price of the Tesla Semi? Is it really worth the services that this vehicle provides? Please share your opinion in the comments section below this video. Thanks for watching our video. Subscribe now so you don't miss the next breaking Tesla update. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to turn on notifications so you never miss our latest videos. We appreciate your support and look forward to seeing you in the next video. Goodbye.
I'm a test engineer for Tesla. My name's JD Price, and we're out here in New Zealand working on Model Y track mode, a new development for the Model Y performance package. So this is full oversteer. All your drifter guys are going to love this kind of setting because as soon as you just tip out, you can just rotate the car around and do some pretty wild maneuvers.
We're here with all of our various platforms working on low mu winter test improvements.
Every car that you see has a Raj on it right now. So these are all Tesla cars moving, doing different maneuvers out and back. Things in green mean we have it. It's a good way to keep track of people.
It's pretty relentless out here with the visibility and the constant dynamic weather.
Where else are you going to find snow in July and August? It's crazy. It's confusing for the body, and it's always been that way.
I think there's a saying, the customer's going to do it, so we have to do it first. You're walking the line between stable and unstable. Tesla's had some of the best safety scores in the game. Stuff like this is a big reason for that.
It's super cool to talk to people in California, send that update halfway across the world. You go on top of a mountain, test their update. That's something that I've never experienced before.
We go all over to test the vehicles to the extreme so that no matter where the customer takes the car, the vehicle's gonna be stable.
We're almost always on a proving ground, testing new software, and we run this thousands of times per software release.
We do everything from driving the car, writing the code, doing the calibration. That feedback loop is super quick. It's cool to think.
A day in New Zealand starts at 5 a.m., wake up.
Go, go, go as soon as you get here.
We're usually here from like 7 to 7. We'll drive back, look at data, prepare builds for the next day, and hopefully grab some dinner. When you come this far, kind of becomes a family.
Everyone loves it. Like, we're doing this because we really want to, you know? It takes a certain personality.
Obviously fun, but also very important, the work that we're doing here.
But it puts a smile on your face every single day, no matter how many weeks you're working here.
Right now we are in UAE, in Dubai Service Center, where we conduct field testing for Tesla.
The climate here is special. It's very warm, so it's part of the reason why we're doing testing here.
We are focusing mainly on mileage accumulation, hot weather related tests, as well as product launch testing. So we like to test these cars here. We also do the same in Norway during the winter. The main goal of this test is to make sure that these vehicles will survive at both extreme conditions, cold and hot. Will be safe for every conditions we have in between these two.
We're actually driving per day between 250 and 400 kilometers to make sure we have a long distance and we stress the car a lot. So now we finished the supercharging, which means we need 100% for this tour today. And we run out to Jebel Jais, to the mountain. Hopefully everything goes good today. Let's see.
I am collaborating with the field quality engineering team from Berlin. We're testing Model Y here, and at the same time we have a US Model X Plaid. Right now we're in Ras Al Khaimah. It's an emirate about 150 kilometers from Dubai.
We are at Jebel Jais. It's the highest place of the UAE.
We are about 1,400 meters above sea level here.
UAE is perfect because the climate is consistent. It's always super hot.
Extreme humidity, extreme heat.
Earlier today it was 51 degrees. So pretty hot.
You don't really find this climate anywhere else in the world.
It can be very dusty one day, so we can have sandstorms or dust storms. It can also get very humid, up to 80–90% humidity sometimes.
The hot climate is really challenging for the vehicle because it has to cool the battery, the drive units, and also